Okay. So we're going to talk today about exponential growth and decay functions. This formula represents exponential growth. The final amount, the initial amount, the rate of growth, always in a decimal form, even though usually it's written as a percentage. And then the time should always be in years. Now this 1 plus r, the rate of growth, this is going to be called the growth factor. And we've talked a little bit about that in a previous lesson 6.3 where we had a times b to the power of x. So the 1 plus r is just kind of like that b. Oops. There we go. Okay, our first example. The inaugural attendance of an annual music festival is 150,000 people. The attendance Y increases by 8% each year. So we want to write an exponential growth function that represents the attendance after T years. So remember, we have the formula Y is equal to A times 1 plus R to the power of T. A, as we said before, is the initial amount. So this is going to start off as the initial amount of 150,000 people. R is the rate, that's 8%, so we want to turn that into a decimal. So that's going to be 0.08. And then as a function of T years, we don't know what that is yet, so we'll leave that in terms of T. And then we can simplify this part here. So that's going to be our equation. And then how many people will attend the festival in the 5th year? And we want to round our answer to the nearest 1,000. So now T is going to be not 5, as many of you would think, but T is actually going to be 4, because 0 is actually going to be the first year, not 1. Remember, anything to the power of 0 is 1. And we already said that the first year was 150,000. So we want to keep that being the same. The 5th year will actually be 4 years after it started. So we're going to make this 4. So Y is going to be 150,000 times 1.08 to the 4, which is 1.3604, blah, blah, blah. Multiply those. And we get this, and we wanted it to the nearest 1,000. So here's our thousands place. So it's going to be 204,000 people at the 5th year. So here's the first do-it-yourself. What I would like you to do is pause the video, give this an attempt, and then you can play the video again to check your work with what I do. Okay, so this one says a website has 500,000 members in 2010. It increases 15% each year. let's write a function that represents the membership in T years after 2010. So this is going to be y equals, we're starting out with 500,000. We increase by 15% each year. And this many years, T years, so it's going to be 500,000 times 1.15 to the power of T. Now for part B, we want to know how many members will there be in 2016. Okay, so let's figure out what T is. In this case, T is going to be 6 because 2016 is 6 years after 2010. So 500,000 times 1.15 to the power of 6. So that's going to be 2.313. So that's going to be and we want to round it to the nearest 10,000. This is a period. The 10,000s places here. So it's going to be 1,160,000 people. Alrighty. Let's take a look at our exponential decay functions. Once again, we have all of the same pieces as our exponential growth function, except for we are now subtracting our rate of decay. And this is still in years. So let's look at our second example. We want to determine whether each table represents growth or decay or neither. So remember, what the first thing we want to do, this is very similar to what we did in 6.3. First, check that your x's are going up by a constant rate, which 0 to 1, 1 to 2, 2 to 3, they are. And then we want to look at our y's. From 270 to 90, 90 to 30, 30 to 10. What are we doing here? We're dividing by 3. But remember, we never want to think about this in terms of division. So how could I think of it in terms of multiplication? It's actually times 1/3. Now, before I determine if this is growth or decay, let's look at our next table. Once again, our x is going up by 1. Let's see what our y's are doing. 5 to 10, 10 to 20. We're multiplying by 2 here. This will represent exponential growth. We're multiplying by a number greater than 1. This will represent exponential, and I missed a bunch of letters there, decay, because we're dividing or multiplying by a number that is less than 1. And it will always be between 0 and 1. Remember, our growth or decay factor can never be negative. So 1/3 is less than 1, 2 is greater than 1, growth, decay. So once again, you have a do-it-yourself. Go ahead and pause the video, try it, and then unpause and check with what my work is. Okay, so for number 2, what's going on here? 64 to 16, 16 to 4, 4 to 1. I am multiplying by 1/4. So this is going to be exponential decay. For number 3, what's going on here? From 4 to 11, 11 to 18, 18 to 25. I'm actually adding 7. So it's neither exponential growth or decay. It's actually linear. All right, now we're going to determine if it's exponential growth or decay by looking at equations. For A, you always want to look here to determine if it's growth or decay. If you remember from our formulas, the decay formula subtracted our rate. It's 1 minus something. So it's always going to be a number less than 1. For growth, we added something. 1 plus something. So it's always going to be a number greater than 1. So in this case, it's greater than 1. So it's going to be growth, because b is greater than 1. Remember, ab to the power of t. Over here, it's decay, because b is between 0 and 1. Remember, b can never be negative. Now, how do I determine the percent of rate of change? Well, in that case, I'm looking just for the r. So I got to get rid of the 1. In the growth part, my growth factor is 1 plus r. In this case, 1 plus r gave me 1.07. So r is 0.07, which as a percent is 7%. Here is 1 minus r. When I have decay, it's 1 minus the rate, which gives me 0.98. Which gives me 0.02 as my rate in decimal form, which will be 2%. All right, example 4. We want to rewrite it to determine if it's exponential growth or decay. And in this instance, I have rational exponents or exponents that are subtracted. So what's going to happen here is I'm going to need to apply my rules of exponents in order to figure this out. So remember, when I have fractional exponents, what's actually happening there? The denominator of the fraction is actually the type of root that I will have. So because this is a 4, this is actually going to be the 4th root of 0.96 to the power of t. And then I can just go ahead and do the 4th root, which is going to give me 0.99. And then looking at this, it's between 0 and 1. So this one will be decay. B, my exponents are being subtracted. How do you subtract exponents? You subtract exponents when they're in a quotient. Remember, if we had something like a to the 4th over a squared, it's a to the 4 minus 2. That's exactly what's going on right here. So we're going to rewrite this. So this is going to be so this is going to be 1.1 to the power of t up above, and 1.1 to the power of 3 down below. Okay, now we need this to be ab to the power of x, or I guess not x in this case, but t. So I need to separate these so that I have an a and a b. Right now I just have a big fraction. So what I'm going to do is take this and remove it out front, right? And it's on the bottom, so it's going to be 1 over 1.1 to the power of 3. And then take this and keep it separate. So all I did was kind of uncombine those fractions, because now these are all numbers. There are no variables. I can do 1 divided by 1.1 to the power of 3, which gives me 0.75. And then 1.1 to the t, and now we can see it's a, b, power of t. Looking at this, it's greater than 1, so this one will be growth. Okay, you have 4 do-it-yourselves again here. Go ahead and pause the video, give them your best attempt, and then we'll come back together. All right, so in looking at this one, this is a number between 0 and 1, so this one's going to be decay. What is the percent rate of change? Well, remember, it's a number subtracted from 1. What's the difference between here and 1? And it's 8. So that's going to be 8%. So I kind of just did that one in my head. But if that is too much of a struggle, you can always set it up as an equation. This would have been the equation I used. 1 minus r equals 0.92. Here, I have a number that's greater than 1, so this one's going to be growth. In this case, how far away is this from 1? 1.2 is 0.2 away, which is going to be 20%, which, once again, if you wanted to set it up as an equation, you absolutely could. All right, these are the more difficult ones. Now I have an exponent that is being multiplied. How do I multiply exponents? That's when you have a power raised to another power. Remember, it's something like b squared then to the 4th, and that's going to be 2 times 4. So in this case, I have 10 times t. So what I can do here is separate them to the 10th, then to the t, because this would become 10 times t, which is what I have here. Then I have to do 1.02 to the 10th. And I get this. This is a number greater than 1, so growth. Here, I'm adding exponents. How do you add exponents? When you have the same bases that are multiplied. So like a squared times a to the 4th is a to the 2 plus, is a to the 2 plus 4. Remember that? So all we're going to do is just separate this. So this is going to be 0.95 to the 2, and then 0.95 to the t. So I know I kind of switched the order. I know it's t plus 2, but the order doesn't matter. 1 plus 2 is the same as 2 plus 1. So if you want to think about this as 2 plus t instead, so the 2 comes first and then t comes after, you can. And there's a reason that I wrote it like this, because now when I do 0.95 squared and I get 0.9, now it's in a times b to the power of t format, which is what I want. And I can look at this, it's less than 1, so that's going to be decay. Alrighty, compound interest formula. We have a lot of parts here. The principal is P. R is the annual interest rate, always in decimal form. T is time in years. And N is the number of times it's compounded per year. It's probably pretty easy to figure this out, but if N equals 1, we get Y is equal to P times 1 plus R to the T, and that's going to be yearly compounded interest. So we're going to use this formula now. So for example 5, I deposit $100 into a savings account. It earns 6% annual interest compounded monthly. Write a function that represents the balance. So I want to figure out what all of these parts are. So I want to find what's my principal, what's my rate, what's my time, what's my N. Okay, my principal is my starting amount. In this case, it's going to be the $100. My rate, it says, is 6%, which I'll write as 0.06 because it's always in decimals. My N, remember, is the number of times it's compounded per year. If it's monthly, that's going to be 12 times because there's 12 months 12 months in a year. And now we just got to put it all together using this formula. So that gives me Y is equal to 100 times 1 plus 0.06 over 12 to the power of 12t. And then I want to simplify this inside part. It's going to be 0.005. So this becomes 1.005 to the power of 12t. I just wanted to write this function. There were no solving because they didn't give me how many years this was going on for. So this is going to be my equation. Alrighty. Getting a little crazy here. So the table shows the balance of a money market account over time. We want to write a function that represents the balance after t years. So remember, our functions are always in the form y equals ab to the power of t or x. A is the starting amount, b is the rate. So let's look at this. Obviously, the year 0, this is my starting amount. Then, how do I get from here to here, here to here, here to here, here to here, here to here? What am I multiplying all of these by? I can divide to figure it out. 110 divided by 100. I'm multiplying by 1.1. 121 divided by 110. Multiplying by 1.1. And even though if you divide these out, it's not perfect, that's okay. It's still very close. Basically, we're multiplying by 1.1 each time. So that's going to be our B. That's going to be our growth or decay factor. In this example, it's growth, obviously. So it's going to be 100 times 1.1 to the power of t. Here, graph the functions from part A, which is this, and example 5 in the same coordinate plane, and compare the account balances. So let's graph this one first. So we have 0, 100. 1 was 110. It's going to be maybe ish there-ish. 2 was 121. All right, that's probably not there then. Maybe like here. Okay, 3 was 133. Like there. 4 is 146. 5 is 161. That got a little too. There we go. All right, let's take a look at the other one. So our other one from example 5, we had 100 times 1.005 to the power of 12t. And we want to do it for the same 0, 1, 2, 3, 4, 5. So I'm going to plug these into my calculator here. If t is 0, I'm going to get 100. If t is 1, 12 times t is 1. So I do this to the power of 12 times 100, and I get 106.17. 2. T is 2. That's going to be to the power of 24. This to the power of 24 times 100 gives me 112. 3. This to the power of 3 times this times this, and I get 119.67. 4, it'll be 12 times 4, 1.005 to that power, times 100, and I get 127. 0.05. And then if t is 5, 12 times 5, 1.005 to that power, times 100, I get 134.89. So let's graph this, 0, 100. So they both have the same starting amount. Then I get 1, 106. 2, 112. 3, 119. 4, 127. 5, 134. So let's compare these. This one is my money market. This one is savings. So how can I compare the money market to the savings? The money market obviously increases faster than the savings. As you can see from our graphs, the top line, even though they both started at 100, the top line is going up quicker than the bottom line. And this last one is a go ahead and do it yourself. So once again, give the video a pause and give it an attempt. Okay, so first you had to create the equation. We're using our compound interest formula. So when we do that, we end up with 500 as my principal. My rate is 9%, compounded monthly, so that's 12 times a year. Simplifying that equation, I get 500 times 1.0075 to the power of 12t. Now I want to graph this. So I'm going to use 0, 1, 2, 3, 4, and 5 for t. Seeing what I get for y. So when I plug it in, 0 for t, you should have gotten 500 for y. 1 for t, 546.9. 2 for t should have gotten you 598.21. 3 will get you 654.32. 4 will get you 715.70. And 5 will get you 782.84. Then you want to graph this. So 0, 500. 1, oh, that's not 500. 450 to 600. So this will be 500 down here. 1, 546. That'll be closer to up here. 2, 598. 3, 654. 4, 715. And 5, 782. Obviously, I put this one in a little bit of a wrong spot. There we go. And there's my graph. So this is what your graph should have looked like, as well as your table. And that concludes our 6.4 notes.